Chapter 25, Calculating pH Changes in a Buffer. A buffer is prepared by adding 0.3 moles of acetic acid and 0.3 moles of sodium acetate to enough water to make a 1 liter solution. Calculate A. the initial pH, B. the pH after you add 5 milliliters of 4 molarity sodium hydroxide, and C. the pH after you add 5 milliliters of 4 molarity sodium hydroxide to 1 liter of water, so not the buffer in the last part. Alright, so step 1, we're going to identify the major species. And we are working with acetic acid, which is not part of our memorized strong acids, which must mean it is weak. We know we have sodium acetate, which is a salt. And as I stated in the last video, we're going to assume that the salt is completely soluble in water. The way you would know it's not is if they gave you a KSP. That would be a good annotation. So if the salt's not very soluble, they'll give you a KSP. Then we have NaOH, which we know is a strong base. All right, step 2, we're going to write out the reaction. Now remember, for these, we need the net ionic ultimately. So let's see, we have CH3COOH, which is weak, so double arrow, and we'll get the acetate ion and the hydrogen ion. We have our salt, which is going to fall apart because it is a salt. And then we have our strong base, which again falls apart completely, dissociates completely because it is strong. Now if I want my net ionic, I had better add these all together. So I'll end up with, and I'm going to write these as their ions now. So CH3COOH, do I split that one up? I do not split that one up because it is a weak substance. We only split up salts that are soluble and strong substances. So that's why I'm going to now split up the sodium from its anion and that other sodium from that hydroxide. And I'll end up with everything I had on the right. Oh man, okay there. Na plus OH minus. Alright, I'm going to start canceling things out here. I have sodium, I have 2 sodiums on both sides. I have acetate on both sides. Now before I cancel out these hydroxides, notice how I have a hydrogen ion and a hydroxide ion on the same side of the equal sign. Those guys are actually going to combine. When you have them on the same side, they will combine to form water. So I won't cross them out. Instead, I'm going to end up with CH3COOH plus hydroxide. It's going to react to form the acetate ion and water. And I mean, since water is on both sides here, I could leave that out. However, this water shows where this hydrogen and this hydroxide go. So that's my net ionic. All right, step 3, well, it depends on what we're doing. Step 3 is asking for the initial pH. So the initial pH means this is before we have added the NaOH. So can I use that net ionic for finding the initial pH? No, we don't use that. Instead, we're going to use this equation right here. If you were to add that equation with the salt equation, you would end up with the same original equation because the sodiums on both sides would cancel out and the acetate ions on both sides would cancel each other out. So the net ionic is the same before the reaction starts as the weak acid reaction. So I'm going to set up an ice chart where I have CH3CO, H reacts to form, and this is reversible, hydrogen plus the salt, the ion that is provided by the salt, and we have ICE. I know that I started off with it's 0.3 moles of sodium acetate in 1 liter. So I know it's the same thing as its molarity, 0.300 molarity. Now for my other ones, let's check. The salt is going to provide, so we've got 0.3 molarity acetic acid. We also have 0.3 molarity of the salt. That salt is going to provide us with this conjugate over here. That is the point of the salt. It's to beef up both sides of this reaction. However, we still don't have any hydrogens. So we don't know what it changes by. You don't have to use X's once we have added in the strong substance. But since this is the before, where it's just the buffer, the plain old buffer, we're going to use X's. So 0.300 minus X, 0.300 plus X. Now that we have done that, this is going to take up a lot of room. I'll just scroll down. Now that we have done that, we are going to plug in our equilibrium. I hadn't written one yet. That could have been an earlier step, but it's okay to do it now. So I know that what is this? This is an acid, so it'll be a Ka, will be the concentration of my hydrogen, my acetate ion over my acetic acid is equal to X times 0.300 plus X over 0.300 minus X. And the Ka for this would have to be given to you, or you'd get it from your charts. 1.76 times 10 to the negative 5. All right, we can use the small x assumption here, or we can try to anyway. So assume x is small, which allows us to get rid of these x's. And if you do that, you're going to end up with x is equal to, it comes out to the same thing as the Ka, which is kind of nice. Now let's just go ahead and prove that this is valid. I need to show that x divided by what it's being compared to times 100 must be less than or equal to 5%, and you end up with 0.0059. So we're good. All right, now that I have x, scroll down a little more, let's now use that to solve for the pH. Now you have to ask yourself, do I need to use the Henderson-Hasselbalch equation? If this is a buffer, then yes, you do. So are we working with a buffer right here initially? Yeah, they have the salt and they have the original weak substance, so we need that Henderson-Hasselbalch. Now, if you were to solve this without using the Henderson-Hasselbalch, you would actually end up with the same pH. It works out okay in this situation. So not a big problem if you do this the other way. But I find it easier to just stick with the Henderson-Hasselbalch. If I know it's a buffer, I don't get confused on when I can use it and when I can't. I just use it all the time and it always works out. So the pH is equal to the pKa, so the negative log of my Ka plus the log of the ion provided by the salt, which was the CH3CO minus, so 0.300 plus X, over the original weak substance, 0.300 minus X. And we know what X is. So if you plug this in your calculators, you will end up getting an initial pH of 4.75. There it is. Okay, so we know that our buffer starts off with a pH of 4.75. Now let's scroll back up and let's see what happens when we start adding a strong base to it. Let's see if the buffer does its job. So what step was I on? I'm on step 6. So step 6. Now we are going to solve for the pH. I'm copying part B here. After adding 5 milliliters of 4 molarity sodium hydroxide. Okay, so if we've done that, if we have mixed in another substance, have I diluted the substance? Yeah, I have. I've diluted it. So we'll have a sub-step here. Now these are all going to be underneath question or part 6. So A, first we need to do the dilution. I'll start with my acetic acid. That one had an initial concentration of 0.300 molarity and an initial volume. I'm going to convert everything to milliliters. So it had an initial volume of 1,000 milliliters. It told us 1 liter, that's 1,000 milliliters. New concentration, I need to add these volumes together, so 1,005 milliliters. M2 is equal to 0.2985 molarity acetic acid. So this is its initial concentration with that new volume, but before it's reacted with the sodium hydroxide. Now for the sodium hydroxide, it was 4 molarity. Ooh, that's a lot. Very strong. However, very small volume. I'm interested to see what happens. Now this one is also 1,005 milliliters. So you end up with 0.0199 molarity sodium hydroxide. And we know that this is equal to the concentration of our sodiums, which is equal to the concentration of our hydroxides, because strong substances completely dissociate. That's an equal sign. Okay, now that I have done that, I am going to figure out what I have left after the reaction has happened. So I'm going to set up an ice chart. And now that I have added my strong substance, I no longer need to use X's. That would be a good annotation. Once the strong substance has been added in buffers, you no longer have to use X's. I am using the net ionic that is based off of a strong substance being mixed with the buffer. I'm using my net ionic right now. So I know from my dilution that my initial acetic acid concentration is 0.2985. Do I have any hydroxides? I do. My strong base provided those. And I know that I also have oh, I missed a little step here, although you could probably figure it out without writing it down. This dilution step here, these same exact numbers work for your NaCH3COO. So I can add onto here, this is equal to the concentration of the Na ion and the acetate ion that is provided by the salt. So over here, I need to say, oh, well, my salt is also providing some of my ions here, so I need to include it. Now I need to look, okay, what is my limiting reactant? What is the smallest number here? And it's coming from the hydroxides. So I'm going to subtract 0.0199 from everything. And you'll end up with 0.2786. Nothing over here. And this one is added, so it's 0.3184. So let's see if this makes sense. We create a buffer, and we want that buffer to stop this strong base from changing the pH. It looks like our buffer absorbed all of those hydroxides. There aren't any left over. So yeah, I'd say we were successful. That buffer stopped those hydroxides from messing with our pH. So now that I know all of these concentrations, I'm going to now solve for the pH. I didn't have to solve for any x's, so I can go straight to solving for pH. And remember, it's a buffer, so if I'm solving for the pH, I must use the Henderson-Hasselbalch equation. So I know that pH is equal to the negative log of the Ka, which is the same one that was given earlier. What was it? 1.76 times 10 to the negative 5. This was a given number. Plus the log of the ratio of the ions provided by the salt. So these are the conjugate base ions over the original acid, all numbers that are coming from equilibrium. And you come out with a pH that's equal to 4.81. This is our answer for part B. Okay, well, let's see. Let's compare that to our old pH we had. Look at that. Our initial pH from part A was 4.75. We added a strong base, and the pH did not change much. That means the buffer did its job. Good job, buffer. So now we're going to do the final part, part C, where we solve for the pH when 5 milliliters of 4.0 molarity sodium hydroxide is added to 1 liter of water. So this is basically a what if situation. What if there was no buffer? This is just the base and the water. What would happen to the pH? So we'll have to do our dilution first. For NaOH, it would be 4 molarity at 5 milliliters. New concentration, 1005 milliliters. So it ends up with a new concentration of 0.0199 molarity. And we know it's a strong substance, so that's the concentration of each of the ions. Now I'm not going to do a dilution for water because water doesn't have concentration, it's just water. It's a liquid. So I'm now going to use this hydroxide concentration to solve for the pH. Do I have to use the Henderson-Hasselbalch here? No, I don't. It's not a buffer, it's just a base in water. So then the pOH is equal to the negative log of the concentration of the hydroxides, which I just found, which is 1.70, which means my pH must be, assuming this is at 25 degrees C, which that's basically all we're working with, you're going to end up with a pH of 12.30. Wow. So if that buffer wasn't in the way and we added those same 5 milliliters of sodium hydroxide, which isn't very much, that pH would have skyrocketed to 12.30. But the buffer did its job and it kept the pH close to 4.75. All right, congratulations. You made it through all of the acid base notebook videos. Yay! Party. See you later.